Hello everyone, my name is Snehas and I'm from the branch of Aeronautical Engineering, and this is my tech talk for the course of flight mechanics. My topic is launching small satellites via autonomous drones. The new frontier, airborne launch of small satellites. The landscape of a space access is rapidly evolving, driven by the increasing demand for small satellites. Traditional rocket launchers, while powerful, often present significant challenges in terms of cost, scheduling inflexibility, and dedicated payload requirements. This is where autonomous drones emerge as a game changer. Cost and flexibility. Traditional rocket launchers are costly and inflexible for small satellites, making dedicated missions prohibitive for many small ventures. Autonomous drone advantage. Autonomous drones offer a flexible, cost and effective alternative for deploying nano satellites, bypassing many traditional launch constraints. New mission possibilities combining unmanned aerial vehicle technology with innovative space launch and mechanics open up a plethora of new mission possibilities and applications. Why use autonomous drone for satellite launch? The rationale behind utilizing autonomous drones for satellites launch is compelling, offering a blend of efficiency, flexibility, and economic benefits that traditional methods struggle to match. First, reduced drag losses. Air launch significantly reduces aerodynamic drag losses compared to ground launches, leading to improved overall launch efficiency and greater payload capacity. Diverse launch locations. Drones enable launches from diverse geographical locations, increasing mission flexibility and allowing for optimal orbital insertion points. Cost reduction. Studies such as one by NLR in 2015 indicate a potential 30% cost reduction compared to ground launched small satellite vehicles, making space access more affordable. Rapid deployment. Drone launches offer rapid deployment capabilities and scheduling independence from large rocket launches, crucial for time-sensitive mission and constellation deployment. Type of drone suitable for satellite launch. The choice of drone platform is critical depending on specific requirements of the mission, payload size, and desirable launch altitude. Various drone architectures offer distinct advantages. Fixed wing drones, characterized by long endurance and high speed, these are suitable for acting as high altitude launch platforms capable of reaching optimal release points. Hybrid VTOL drones, combining vertical takeoff and landing capabilities as extended flight ranges, offering operational flexibilities from various terrains. Multi-rotor drones, while offering precise positioning and hover capabilities, their utility is often limited by payload capacity and endurance, making them less ideal for higher altitude launches. An illustrative examples come from an NLR study where an F-16 aircraft was successfully used as a carrier for a solid propeller nanosatellite launch vehicle, demonstrating the viability of aircraft-based launch systems. Flight mechanics from drone release to orbit insertion. The journey from drone release to orbit insertion is a complex ballet of physics and engineering, requiring precise control trajectory optimization to overcome atmospheric resistance and achieve desired orbital parameters. High altitude ascent. This drone ascends to a high altitude, typically between 10 to 15 kilometers, to significantly reduce atmospheric drag on the launch vehicle. Mid-air release. The satellite launch vehicle is released mid-air from the drone, following by the ignition of its solid rocket motors. Trajectory optimization. The trajectory is meticulously optimized for velocity, flight path angle, and altitude, ensuring the vehicle reaches low Earth orbit efficiently. Multidisciplinary design. A multidisciplinary design optimization approach is employed, balancing aerodynamics, propulsion system performance, and mass constraints for optimal mission success. Key flight controls and navigational technologies. Achieving a successful satellite launch through autonomous drone hinges on sophisticated flight control and navigation systems. These technologies ensure precision, stability, and reliable operations throughout the entire launch sequence. Onboard sensors, utilization of advanced microelectromechanical systems, accelerometers, gyroscopes, and magnetometers for accurate altitude and position estimation of both the drone and launch vehicle. Satellite communication. Robust satellite communication links are essential for real time command and control, enabling operators to monitor and direct the launch sequence from the ground. Autonomous control algorithms. Integration of sophisticated autonomous flight controls to process sensor data, ensuring stable and controlled flight during critical phases, including high speed release and ignition. GPS and inertial navigation. Combined use of global positioning system and inertial navigation system to maintain precise launch parameters, crucial for accurate orbital insertion. Challenges in autonomous drone satellite launch. While promising, the autonomous drone satellite launch concept prevents several significant challenges that require innovative engineering to rigorous testing to overcome. These challenges span from mechanical stresses to regulatory hurdles. Flight stability. Maintaining stable flight and precise orientation of both the drone and the launch vehicle during the dynamic phases of high speed release and ignition is technically demanding. Thermal and mechanical stress. Managing the extreme thermal and mechanical stresses encountered by the small satellite and the launch vehicle during ascent and separation is paramount to mission success. Communication reliability. Ensuring reliable and secure communication links for command, control, and telemetry in the dynamic and challenging environmental of high altitude flight is critical. Regulatory integration. Navigating the complex regulatory landscape and integrating drone based launch operations into existing airspace management systems poses a significant challenge. Case study. Nano satellite launch vehicle on F-16 carrier. The NLR study involving a F-16 fighter jet as a carrier for nano satellite launch vehicle provides a compelling demonstration of the feasibility and economic advantages of airborne small satellite launches. Vehicle design. A three-stage solid rocket vehicle was designed to fit seamlessly within the external fuel tank contours of an F-16 aircraft, optimizing aerodynamics and integration. Payload capabilities. The system demonstrated the capability to deliver a 10 kg payload to low Earth orbit, with the launch vehicle mass being 70% lower than comparable ground launched equivalents. Cost efficiency. The estimated launch cost was approximately 1.9 million euros per launch, representing a significant 30% reduction compared to traditional ground-based launch options. Proof of concept. This case study powerfully illustrates the technical feasibility and substantial cost benefits of implementing airborne small satellite launch methodologies. Future outlook autonomous drone launch systems. India's in India. India's small satellite market is ripe for distribution disruption, with autonomous drone launch systems offering a pathway to meet the increasing demands for flexible, low cost access to space. This approach aligns perfectly with India's ambiguous space agenda. Growing market demand. The expanding Indian small satellite market launch necessitates flexible and a cost-effective launch option for various applications. Integration with Indian UAVs. Potential for seamless integration with existing Indian UAV platforms and collaboration with national space programs like ISRO. Rapid constellation deployment, enabling swift and efficient deployment of satellite constellations for communication, Earth observation, and diverse scientific missions. Technological advancements. Continuous advances in drone autonomy, robust satellite communication, and efficient propulsion systems will be key drivers for off adoption. Conclusion. Revolutionizing small satellite launch with autonomous drones. The convergence of autonomous drone technology and satellite launch mechanics represent a pivotal shift in how we access space. This innovative approach promises to democratize space access, particularly for the burgeoning small satellite sector. Aerospace innovation. Autonomous drone launches blend cutting edge aerospace innovations with the critical need of modern satellite deployment. Precise and cost effective. Advanced flight mechanics and control technologies ensure precise and cost effective access to orbital space. Democrat- Democratizing space access. This method supports India's ambiguous space programs by making space more accessible and affordable. The sky as launchpad. The boundaries of the sky are transformed into launchpads for the next generation of small satellites, propelling us into new era of space exploration. Thank you.